Now that we define a relation, we're interested in analyzing some important properties on the relations. We're going to say that a relation like R, so let be a relation on set A. We say that this relation is reflexive. The relation R is called a reflexive relation if and only if for any x in A, x is in relation with itself. For all x in A, x is in relation with x. For example, remember we talked about divisibility. X divides itself. Am I right? So divisibility is an example of a reflexive relation. You see that a relation is symmetric. So relation R is called symmetric if and only if for all x and y in set A, if x is in relation with y, then you can conclude that y is also in relation with x. Again, you can talk about divisibility, you can talk about equality if x divides y. It's not always the case that y divides x. So if 2 divides 4, you cannot conclude that 4 divides 2. So divisibility works for reflexive relation, but not for a symmetric relation. An example of a symmetric relation is, for example, equality. If A is equal to B, then for sure you can say that B is equal to A. If X is equal to Y, then you can for sure say that Y is equal to X. So equality is one of the examples of a symmetric relation. Number 3, we say that a relation like R is called transitive relation if and only if for all x, y, and z in set A, if x is in relation with y and y is in relation with z, then for sure you can say that, hey, x is in relation with z. One example that you saw multiple times in algebra is being less than. If x is less than or equal to y, and y is less than equals to z, then for sure you can conclude that x is less than equals to z. So less than or equal to as a relation is a transitive relation. If a relation is reflexive, symmetric, and transitive, you call it an equivalence relation. Note that. An equivalence relation is a relation which is reflexive, symmetric, and transitive. Divisibility, it is reflexive, but it's not symmetric. It is transitive. But since it's not symmetric, it's not an equivalence relation. Equality. Equality is reflexive, symmetric, and transitive. A relation like equality is an equivalence relation. Being less than or equal to, this guy is not symmetric, so it doesn't satisfy the condition for an equivalence relation. So not all relations are equivalence relations. You need to check each one of these separately. Let's take a look at this example here. In this example, we have the following set example. Let's set A be defined as 0, 1, 2, 3, and we're going to define the following relations. The very first relation is R, which is defined as, well, you have 0 and 0. You have 0, 1. You have 0, 3. 1, 0, 1, 1, 2, 2, 3, 0, and 3, comma 3. This is relation R. Now we're going to define relation S. This relation is defined as 0 and 0, 0, 2, 0, 3, 2 and 3, and your last relation, relation T, has only two members, 0 and 1, 2 and 3. So let us analyze this relation R. Is the relation a reflexive relation? Take a look at the loops. You have 0 related to 0. You have 1 related to 1. Take a look at the definition. For all, for every x in A, x must be related to itself. You must have a loop. 1 is in relation with itself, 2 is in relation with itself, 3 is in relation with itself. So R is reflexive. Very good. Being symmetric says, hey, if x is in relation with y, then you can conclude that y is in relation with x. So if x and y are related, y and x needs to be related as well. Take a look. 0 is related to 1. Also, 1 is related to 0. So far, so good. What about here? 0 is related to 3. Also, you have 3 related to 0. What else? You don't have anything else. You had 0 and 1. You see 1 and 0. You had 0 and 3. You also see 3 and 0. So it is reflexive and symmetric. What about being transitive? Transitivity says, hey, if X is related to Y and Y is related to Z, so if I have two pairs with this relation, then I need to conclude that the very first element and the last element are connected as well. Take a look. I have, let's see. Let us find all of the relations, X and Y, Y and Z's. I have 1 connected to 0. I have 0 connected to 3, but I don't have 1 and 3 in this set. So take a look. 1 is related to 0, and 0 is related to 3, but 1 is not related to 3. Okay, I found the one that makes R not to be transitive. So my R is not transitive. So R not transitive. Okay. Now let us move on and talk about relation S. Okay, is S reflexive? Can you conclude that for all X values in A, X has a loop? I have 0 and 0, I'm fine. 0 is related to 0, we're good here. But what about 1 and 1? What about 2 and 2? What about 3 and 3? 1 is not related to 1. So it's S, so 1 is not related to 1 over S in this relation. So not S, not reflexive. One example is enough, everybody. What about being symmetric? Okay. For example, I have 0 related to 2, but 2 is not related to 0. 0 is related to 2, but 2 is not related to 0. So S not symmetric. What about being transitive? Guys, take a look. If you have X related to Y, Y related to Z, you need to see the relation between the very first and the last element. Okay. 0 is related to 0, 0 is related to 2, 0 is related to 2. So far, so good. 0 is related to 0, 0 is related to 3, 0 and 3 are in the set. Okay, do I have anything else? 0 is related to 2, 2 is related to 3, 0 is related to 3, which is just right here. I don't have anything else. I need 2 pairs. And for those pairs in this set, the very first element and the last element are connected. So S is transitive. S is transitive. Now let's move on to the last relation, relation T. Okay, obviously this guy is not reflexive. 0 and 0 is not there. So you can just easily say that since there is no loop, 0 is not connected to 0. T is not reflexive. What about being symmetric? 0 is connected to 1, but 1 is not connected to 0. 0 is related to 1, but 1 is not related to 0. So T not symmetric. What are being transitive? Well, do I have two pairs that have this relation? 0 is connected to 1. Well, I don't see anything else. 2 is related to 3, but I don't see anything else. So it means that all of those conditions are satisfied. T is transitive.